In the last two videos, we had talked about the real numbers, and in relation to the real numbers, we discussed how every composite number can be expressed as a product of its prime factors. And then we also talked about the fundamental theorem of arithmetic, wherein we said that every composite number can be represented as a product of its prime factors. And this representation of the composite number in terms of the product of prime factors is going to be unique, except for the fact that the order of the prime factors in which they are multiplied, that can change, but the prime factors itself is going to be unique. Okay, we talked about that, and we also did some exercises relating to the fundamental theorem of arithmetic. Now we will extend our discussion further to irrational numbers. And irrational numbers is not something new, because you have studied irrational numbers in your class 9, and you talked about what are irrational numbers, and we have also seen in class 9 several properties of irrational numbers. However, what we did not do in our class 9 discussion of irrational numbers is we did not see how to prove whether a number is irrational. So the proof of irrationality is something that we had not seen in class 9, but that is something we are going to do in class 10. So we are going to see how to prove that a number is irrational. But before we go into that, let us quickly recall what is an irrational number. An irrational number is something that can be expressed in the form of p by q. So an irrational number can be represented in the form p by q, where p and q are integers, and the denominator q should not be equal to 0, right? So this is the definition or the condition that a rational number must satisfy. Okay, so a rational number is something which can be represented in the form of a ratio p by q, where p and q are integers and q is not equal to 0. So this is the definition of a rational number. Okay, and any number that cannot be represented in this form as a ratio of integers, p and q, then such numbers would be called as irrational numbers. And typically the examples of irrational numbers that we had seen earlier are like square roots of prime numbers. So irrational numbers cannot be represented in the form p over q with p and q integers and q not equal to 0. Okay, so for irrational numbers it is not possible to have this representation. So the examples of irrational numbers that we had seen, examples are like square root of 2, square root of 3, square root of 5. We have seen the number pi as being irrational, which is, pi is a constant 3.14 and so on, right? So pi is a non-terminating decimal. So therefore pi cannot be represented in the form p by q. So in general, what we notice is that for any prime number p, in general, for any prime p, the square root of p is irrational. Okay, so this is a statement, okay, that we will remember. But then we have still not seen how to prove that square root of p is irrational. Okay, this is what we are going to do in today's video. So we will see a method of how to prove that a particular number is irrational or not. And to do that, we are going to use a technique called as the technique of contradiction, or the method of contradiction. So we are going to, when we are asked to prove that some number, let's say root 2 or root 3, is irrational or not, we will first assume that it is rational. That means it can be represented in the form of p by q, where p and q are integers. And then we will see that by assuming that it is rational and we take the idea forward, we will see that some basic property will be contradicted. And because of that contradiction, we will say that our initial assumption that that number was rational is incorrect. So therefore, our initial assumption has to be changed. So we will conclude that the number is in fact not rational, and therefore it is irrational. So that is what is called as the method of contradiction. But before we go into the method itself, we will use a particular theorem again for proving irrationality of a number, and that theorem is derived, or is an extension of the fundamental theorem of arithmetic. And what this theorem says is that if we have some prime number p, and if that prime number p divides another positive integer square, that is a square, then that prime number also divides a. So we will use this idea in proving the irrationality of numbers. So if a prime number p divides a square, then that prime number p also divides a, and where a is some positive integer. And again, let's try to prove this condition first. So let's say we have a number a, which is a product of its prime factors. A is a positive integer, so it is a composite number. And from the fundamental theorem of arithmetic, we know that the number a can be represented as a product of its prime factors. So p1, p2, p3, and so on up to pn are the prime factors of a. So a is represented as a product of its prime factors. So therefore, a square will be the product of the prime factors multiplied with themselves. So we get a square as p1 square into p2 square into p3 square up to pn square. Now, since it is given to us that the prime number p divides a square, we know that from the fundamental theorem of arithmetic that each of these p's are unique. That means the product of the prime factors, that in the individual elements that we have in the prime factors, they are all unique, and there can be no other new number involved in that product. So if p divides a square, that means that p must be one of the p1, p2, p3. It must be one among the p1, p2, p3, and pn. So the p that is dividing a square must be one of the numbers from p1, p2, p3, and pn, and so on. So therefore, we say that since a is a product of the prime factors p1 to pn, the number p must be one of these numbers p1, p2, and pn. So therefore, we can conclude that p also divides a. So this is the idea we are going to use in proving the irrationality of a number. So to summarize, if a prime number p divides a square, then we know that the same prime number p also divides the number a. Okay, and this is the idea we are going to use in proving the irrationality of any number. So let's go ahead and do an example. So we will use the method of contradiction again, as I said before. And the method of contradiction is nothing but we have to prove that a number is irrational, but we will assume that it is rational. So let's consider root 2 is rational. Okay, so we are going to assume the opposite. Okay, so we have to prove it's irrational, but we will consider that it is rational. So if it is rational, that means we can represent root 2 as ratio of integers a by b. Okay, so because a rational number can be represented as a ratio p by q or a by b, where a and b are integers and b, the denominator, is not equal to 0. So a and b are integers, so a and b are integers, and a and b have no common factor between them other than the number 1. That means we have reduced this ratio such that a and b has only a and b have only 1 as a common factor. That means a and b are co-prime. So in this case, a is an integer, b is an integer with no other prime common factor between them other than the number 1. And since we are assuming that root 2 is rational, so we are able to represent root 2 as a ratio of integers. This is our assumption. And let's see if this assumption leads to something which is contradictory. So based on this, we can now write we can take the b to the other side, so we will get b root 2 as equal to a. So we have basically taken the b to the other side, so b into root 2 is now equal to a, and then we can square this entire equation. So we'll get b square root 2 into root 2 is going to be 2 is equal to a square. So that's b square into 2 is equal to a square, or we can rewrite that as 2b square equals a square. Now, by looking at this expression 2b square equals a square, we can deduce that a square is divisible by 2. So since 2b square is equal to a square, it means that a square is divisible by, let me write that properly, a square is divisible by 2. So if a square is divisible by 2, it follows from the previous theorem that, so therefore we can also say that a is also divisible by 2. Now, this is contradicting the fact that we have taken here a and b to be integers such that there is no common factor between them other than the number 1. But now we are seeing here that a is divisible by 2. Okay, so what we have deduced here is a is divisible by 2. Let's see what happens because of this. If a is divisible by 2, that means we can write a as a multiple of 2, right? So if a is divisible by 2, then we can write a as a multiple of 2, that is a equals 2 times something. So we can write a as 2 times something. We'll call that something as c, where c is another integer, where c is another integer. So what we are getting here is since a square is dividing 2, that means a is also dividing 2, and therefore we can represent a as a multiple of 2. So 2 times c is the representation of a. Now we can substitute that value of a, which is a equals 2c, in our relationship here. So we have this relationship here that 2b square equals a square. So we will take this relationship 2b square equals a square, but we now know that a is a multiple of 2, so we have a in the form of 2c. So in place of a, we will substitute 2c and see what happens. So we already have the fact that a is divisible by 2. Now we will substitute a equals 2c in 2b square equals a square. So since a is 2c, we can write this as 2c the whole square, which is 4c square. So we get here that 2b square equals 4c square, or we can divide this whole thing by 2 and get b square equals 2c square. So what this equation is telling us is that b square is divisible by 2. So from the above expression, since b square is 2 times c square, it means that 2 divides b square. So therefore we can say that 2 also divides b from our previous theorem. So if any number p divides the square of a number, then that number also divides the number itself. So that's the theorem that we have seen earlier, right? So if p divides a square, then p also divides a. So similarly here, if 2 divides b square, then it means that 2 also divides b. Now what we are noticing is that we are seeing that b is divisible by 2, and we had earlier seen that a is also divisible by 2. And this is a contradiction, because when we started off our first expression of writing the square root of 2 in the form of a by b, we had considered that a and b are integers with no common factors between them other than the number 1. But here we have a is divisible by 2. That means a is having a factor 2. And here we have b is divisible by 2. That means b is having a factor of 2. And this is contradicting our initial condition that a and b have no common factors other than 1. So we have a factor 2 for a and a factor 2 for b as well, which is contradicting that a and b have no common factors other than 1. So we can write that therefore a and b, therefore a and b have at least 2 as their common factor. Okay, but this violates that a and b have no common factors other than 1. Okay, so let me write that statement. So what we see is that we started off with our assumption that a and b have no common factors among them other than the number 1, but we found out that a is divisible by 2 and so is b. Okay, so that means a and b have 2 as their common factor, and this is a violation of our initial assumption that there are no common factors for a and b other than the number 1. So this is a contradiction, and this contradiction is happening because our initial assumption that root 2 is rational is incorrect, and because of that we can conclude that our initial assumption is wrong, and therefore root 2 is irrational. So it means that, so I'll write it here at the top. So therefore our initial assumption that square root of 2 is irrational is incorrect. So therefore, okay, our initial assumption is rational. Okay, we assume that initially we assume that root 2 is rational. Okay, so our initial assumption that root 2 is rational is incorrect. So therefore root 2 is irrational. Okay, so this is what we call as the method of contradiction, proving by contradiction. So we started off by considering that root 2 is rational, and for a rational number it can be represented as a ratio of integers, and we considered that those integers do not have any common factor other than 1, but then we went on to show that both the integers a and b have a common factor 2, at least one common factor 2, and this is violating our initial assumption that there is no common factor. So therefore we conclude that our initial assumption that root 2 being rational is incorrect. So therefore we will conclude that, or we will prove that square root of 2 is irrational. Okay, so this is the method of contradiction by which we are proving that square root of 2 is irrational. So let us do one more example here, and it will become much clearer. So we will take one example from the exercise problem where we have to prove that square root of 5 is irrational. So we will proceed as before by using the method of contradiction. So for that we will first consider the given number root 5 as a rational number. So if it is rational, we can write that number as a ratio of integers a and b. So a and b are integers and b is not equal to 0. Okay, this is our assumption. So that means like before, we can move the b to the other side, so we get b root 5 equals a, and we can square this equation and we get 5b square equals a square. So what we see is that because of this relationship, a square is 5 times b square, or in other words, we can deduce that 5 divides a square. So if 5 divides a square, from the theorem 1.2, we can say that therefore 5 also divides 8. Okay, that's our first condition that we get. Okay, so we are getting the information that 5 is dividing a, that means a is divisible by 5. Now, since a is divisible by 5, we can represent a as a multiple of 5. So we can represent a as a equals 5 times something. So 5 into something, we will call that something as c. So where c is some integer, where c is an integer. Okay, so now what we can do is we will substitute this value of a as 5 times something in our original relationship between a and b, which we have here. So in this equation, we will substitute a equals 5c. So when we put a equals 5c, we get 5b square equals, in place of a, we will put 5c the whole square. That's a square, right? So since a is 5c, it's 5c the whole square, which is 25c square. So we can write b square as 5 times c square. Or from this relationship, what we get is that since b square is a multiple of 5, we can deduce that b square is divisible by 5, or in other words, so this means 5 divides b square. 5 divides b square, and therefore from our theorem we know that 5 also divides b. So now what we get is we see that we are getting a relationship that 5 divides a. So we have here, that means a is divisible by 5, and here we are getting 5 is dividing b as well. That means b is also divisible by 5. That means a and b have a common factor of 5. But we started off here that a and b are integers, with b not equal to 0 and a and b have no common factor other than 1. Okay, so that's the other assumption that we had in the beginning itself. Okay, a and b are integers and b not equal to 0 with a and b have no common factors other than 1, right? But here we see that a is having a factor 5 and so is b. Okay, both are having a common factor of 5. So both a and b are divisible by 5. That is a and b have at least 5 as a common factor. So what we can conclude from here is that this is violating our initial assumption that a and b have no common factors. So this violates or contradicts our initial assumption So therefore, it means that, root 5 considered as rational at the beginning is incorrect. So our initial assumption is being contradicted here. So we conclude that. So therefore, root 5 is irrational. Okay. So we are proving the number being irrational by contradiction. Okay, so we initially assume that it is rational, and for a rational number we can represent it in the form of a by b, where a and b are integers with no common factor between them other than the number 1, and thereafter we go on to show that a and b have some common factor other than number 1. In this case, a and b have a common factor 5. Okay, so this is a contradiction that a and b have no common factor other than 1. There is an additional common factor at least of 5. So therefore we will say that our initial consideration that root 5 being rational is incorrect, and from that we prove that square root of 5 is indeed irrational. So when you're proving these things, you have to have a clear idea as to how you are presenting the argument here. Okay, so you have to first have a clear representation of your initial assumption, and then go on to show that that initial assumption is being contradicted or violated through some other arguments. So our initial assumption that the ratio a and b, the ratio of a and b has no common factors other than 1 is being violated. So we need to show somehow that the numerator and denominator terms a and b have some additional common factor other than the number 1, and which that contradicts our initial assumption of considering that number as being rational. Okay, and from that we go on to say that because of the contradiction, our initial assumption is incorrect. Therefore we will make the correct decision about that number, which is the opposite of our initial assumption. So the initial assumption was rational, so the correct decision would be the opposite of rational, which is irrational. Okay, this is the procedure we are going to apply for proving any number to be irrational. Now we have taken individual numbers here. In the previous case we took root 2. 2 is a prime number. Square root of 2 is irrational. Okay, and in general, as we mentioned earlier, the square root of any prime number is irrational. So the value p can be 2, 3, 5, 7, 11, 13, whatever. The square root of any prime number is irrational, and we can go on and prove that the square root of any prime number is irrational by the method of contradiction. The other thing that we have is that if we have a rational number and an irrational number, then the sum or difference of a rational number and irrational number is also irrational, and this is something that we have seen in our class 9 as well. So we can go ahead and prove that the sum or difference of a rational number and an irrational number is indeed irrational. So the number 5 here is a rational number, and the square root of 3 is an irrational number. So we have the difference of a rational number and an irrational number, and this is going to be irrational, but we have to prove this. And to prove this, we are once again going to use the method of contradiction. So we will consider, okay, I'm not going to write all the steps now, okay. Consider 5 minus square root of 3 as rational. Now if it is rational, then we can represent 5 minus root 3 in the form of a over b, where a and b are integers with no common factor other than 1. So this is what we are going to do. It's the same procedure, okay. So we can now write 5 minus a by b. Okay, I'm just taking the a by b to the left side and the minus root 3 to the right side. So 5 minus a by b is equal to root 3, and this is what we have here. And since we have b in the denominator, we can take the LCM as b, and when we take the LCM as b for the left hand side, so we'll have 5b minus a equal divided by b equals root 3. Okay, so we have taken b as the LCM. So here in the denominator we have 1, so 1 times b is b, b into 5 is 5b, minus b goes into b 1 time, and 1 into a is a. So it's 5b minus a divided by b equals 3. And since we have considered 5 minus root 3 as a rational number, so we have represented that as a ratio of integers. So that means we are considering a and b as integers. So we write, since a and b are integers, that means 5b minus a is integer, and b already is integer, b is also integer. So that means 5b minus a divided by b is a ratio of integers. So this is the left hand side, right? So this is the LHS. Okay, the left hand side is a ratio of integers, and if it is the ratio of integers, it means that the LHS is rational. But we already know that, square root of 3 is irrational. All right, excuse me for my handwriting. Let me rewrite that a bit clearly. Square root of 3 is irrational. So that means the right hand side of our expression, so we have this expression here. Okay, so we find that the left hand side 5b minus a divided by b is rational, but on the right hand side we have root 3, and we know already that square root of 3 is a prime number, and the square root of any prime number is irrational. So we are getting the left hand side as rational and the right hand side as irrational. So that is a contradiction. Okay, we are saying that left hand side equals right hand side. How can it be equal if the left hand side is rational and the right hand side is irrational? So it violates this equality here. So that means this contradiction is happening because our initial assumption that 5 minus root 3 being rational is incorrect. So this is a contradiction. So LHS is rational, RHS is irrational. So we have LHS being rational, RHS being irrational. So this is a contradiction. Okay, this is a contradiction. And why is this contradiction happening? It's happening because it is due to our initial assumption that 5 minus root 3 is due to our initial assumption that 5 minus root 3 is rational is incorrect. So therefore we can conclude that 5 minus root 3 is indeed irrational. Okay, so we start off by considering that the given number is rational, and then we will go on to prove that some condition is being contradicted. And using that contradiction, we will argue that our initial assumption is incorrect, and therefore we will make that correction. So we initially assume that it is rational, and because of the contradiction, we say that our initial assumption is incorrect. So 5 minus root 3 is irrational is incorrect. So therefore, the correct answer or the correct decision should be 5 minus root 3 is irrational. Okay, so we have proved that our initial assumption of that number being rational is incorrect. So therefore, we conclude that it is indeed irrational. Okay, so that's another example of proving irrationality. But in this case, we have taken an example where we have taken the sum or a difference of a rational and an irrational number. In this case, it's the difference. So 5 is a rational number and square root of 3 is an irrational number. So we have a difference of a rational number and an irrational number. So instead of minus, if we had plus, it would be the sum. In either case, instead of 5b minus a by b, it would have been 5b plus a by b if it was sum. In either case, the LHS will be a ratio of integers that will give us a rational number, but the RHS will remain irrational. So the equality will not hold if the LHS is found to be rational and the RHS is found to be irrational. So that cannot be possible. We cannot have the left hand side equal to the right hand side and then go on to say that the left hand side is a rational number but the right hand side is an irrational number. So we can't have both the statements to be true. That's a contradiction. So because of this contradiction, we will argue that our initial assumption of considering that number being rational is incorrect or invalid. So therefore that number is irrational. Okay, so let's go ahead and see some more examples. So we have another example here. Just as we have seen that the sum or difference of a rational number with an irrational number is irrational, another thing we have seen in our class 9 is that the product and quotient of a non-zero rational number and an irrational number is also irrational. So we are going to, in this case, prove that the product of a rational number with an irrational number is irrational. So 3 is a rational number and square root of 2 is an irrational number. So we will prove that the product of a rational number with an irrational number is irrational. And again, we will use the method of contradiction. So we will again consider 3 root 2 as rational. So that means we can write 3 root 2 in the form of a over b, where a and b are integers with no common factor other than 1. Okay, so we can now take the b to the other side, or we can write this root 2 as a by 2b. Okay, so we have a by 3b, that is right, it's 3 root 2. So let me make that correction. So we just take we're taking the 3 to the other side, so it's square root of 2 is a divided by 3b, that's 3b, a divided by 3b. Now what we notice is on the left hand side we have root 2, so LHS is root 2, which is irrational. We know root 2 is irrational. Okay, but what do we have on the right hand side? RHS, the right hand side of the equation, is a divided by 3b, and we know that a and b are integers. So therefore we can say that a divided by 3b is a ratio. A is an integer, b is an integer, 3 is also an integer. So that means a divided by 3b is a ratio of integers. And that implies that a by 3b is rational. So we have LHS irrational and RHS is rational, and we have LHS equal to RHS. So this is a contradiction. How can a rational number on the an irrational number on the left hand side and a rational number on the right hand side be equal to each other? So this is a contradiction. This is a contradiction. Okay, so therefore our initial assumption that 3 root 2 is rational is incorrect or invalid. So we will conclude that therefore 3 root 2 is so let me write the full statement. So we have our initial assumption which we consider 3 root 2 as rational to be an incorrect assumption, and that is why we are getting this contradiction. So therefore we will conclude that, so therefore 3 root 2 is irrational. Okay, the contradiction arose only because our initial assumption was incorrect. Okay, so we have seen a few examples here of how to prove that a number is irrational using the method of contradiction. Let's do a couple more examples from the exercise. So here we are going to use the sum of a rational number with an irrational number. So we have 3 is a rational number. 2 is also a rational number, but root 5 is irrational number. So we have seen that product of a rational number with an irrational number is irrational. So 2 root 5 is going to be irrational, and this irrational added to a rational number is also going to be irrational, and we need to prove that. So to prove that, we will consider that it is rational in the first place. So our starting point is we will consider that it is rational. So consider 3 plus 2 root 5 is rational. So if it is rational, then we can represent 3 plus 2 root 5 as a ratio of integers a and b, okay, where a and b have no common factor other than 1 and b is not equal to 0. Okay, that's the general statement, so we will take it as a given for that. Okay, henceforth when we discuss this, I will not explicitly state that. So 3 plus 2 root 5, the rational number, can be represented as a ratio of integers with no common factors between them other than the number 1, and the denominator is not equal to 0. Now we can rewrite this expression as 3 minus a by b, 3 minus a by b Okay, I'll just rewrite this in a different way. So we'll keep the 2 root 5 on the left hand side. So we'll have it as 2 root 5 on the left hand side. On the right hand side we have a by b, and we'll also take the 3 to the other side. So that will be a by b minus 3, which we can write as or we can write root 5 as, we'll take the 2 also to the other side, root 5 as a by 2b minus 3 by 2. Okay, so I've just taken the 2 also to the other side. So since 2 is multiplying here, when it goes there it is going to divide. So we have root 5 as a by 2b minus 3 by 2. And what we notice here is that, again, on the left hand side we have root 5. So let me write LHS is root 5, which is irrational. Okay, we know that. But on the right hand side, RHS, we have a by 2b minus 3 by 2. And we know that a is an integer, b is also an integer. So therefore, let me write, since a and b are integers, let me write it on the next line, are integers, a over 2b is rational. Okay, so a over 2b is rational because a is integer, b is also an integer, the number 2 is also an integer, obviously. So therefore a by 2b is a ratio of integers, therefore a by 2b is rational. So if a by 2b is rational, we also have here 3 by 2, which is also a rational number. So therefore we can say that a by 2b minus 3 by 2 is also rational. Why? Because a by 2b is rational. So let me okay, that's a rational number, and 3 by 2 is also rational, so that's also rational, that's also rational. And the difference of a rational number with another rational number is also rational. Okay, only if one of them is rational and the other is irrational, only then it will be irrational. If both are rational, then we are going to get it as a rational number. So a by 2b is rational, 3 by 2 is also rational. So therefore the right hand side is rational. So now what we have is, on the left hand side we have it as irrational, and on the right hand side we have it as rational. So the left hand side is equal to right hand side, but left hand side is irrational whereas right hand side is rational. So this is a contradiction. So this is a contradiction. And why is this contradiction happening? This contradiction arises, okay, arising due to our incorrect assumption that 3 plus 2 root 5 is rational. Okay, so that's our incorrect assumption. Okay, that 3 plus 2 root 5 is rational. So therefore we have to make that correction. So the correct answer, the correct assumption would have been, so therefore 3 plus 2 root 5 is irrational. Okay, so similarly we can do one more example. So let's do one more example from the exercise, and we have 1 over root 2. So here in this case it is a quotient. Okay, it is a division of a rational number with an irrational number. So we have on the numerator the number 1, which is rational, and on the denominator we have root 2, which is irrational, and we have to prove that 1 over root 2 is irrational. So we will start with our in the same procedure by considering 1 over root 2 as a rational number. So therefore we can write 1 over root 2 in the form of a by b, where a and b are integers with no common factor between them, and b is not equal to 0. So in other words, we can write this as okay, so we can write this as b is equal to root 2 times a, and we know that a and b are integers. So since a and b are integers, okay, we know that again on the left hand side here we have b, which is basically as b over 1, which is rational. But on the right hand side we have root 2 times a, and since a is an integer, so since a is an integer, root 2 times a is going to be the product of an irrational number with a rational number. So root 2 times a is irrational. Okay, so therefore what we get is we have the LHS as rational. Okay, and we already have that. So now we have the RHS as irrational. So this is a contradiction. We have LHS as rational, whereas the RHS is irrational. So this is a contradiction. So this is a contradiction. So therefore we can conclude that 1 over root 2 is irrational. Okay, so we have proved that 1 over root 2 is irrational. So we have seen several examples as to how we can prove a given number is irrational by using the method of contradiction. So there are we start off with an assumption that the given number is rational, and then we go on to show that there is some contradiction in some general relationship that is known to us. So because of that contradiction, we will show that our initial assumption is incorrect, and thereafter we'll make a conclusion that the correct assumption should have been that the number is irrational. So this is the method of contradiction, and we have seen several examples of proving that a number is irrational by using this method of contradiction. Okay, so that brings us to the end of this particular chapter, chapter 1 on real numbers. So the first part of the chapter, which we discussed in the previous two videos, we discussed the fundamental theorem of arithmetic, and using the fundamental theorem of arithmetic, we showed that any composite number can be expressed as a product of its prime factors, and we used that representation to find the LCM and HCF of those numbers, and we did some problems based on those ideas. And in today's videos, we have seen how we can prove that a given number is irrational by using the method of contradiction. Okay, we will move on to the second chapter in the next video, and the second chapter deals with polynomials. Okay, so we will talk about polynomials from the next video onwards.